Origin's Design of Experiments app can design an experiment, fit a model to collected data, and find the best factor settings that optimize responses. In this video, we will optimize responses under a Box-Behnken design. A company is developing a new facial cream design to meet two objectives: maximize hydration and target a neutral pH of 7. During the product development phase, the formulation team identified 3 key variables that influence hydration and pH level: the type of oil used, choice of emulsifier, and selected fragrance. All 3 are measured as a percentage of the ingredients that make up the facial cream. A response surface design can be used to model the relationship between the response variables, hydration and pH level, and the 3 factors of interest: oil, emulsifier, and fragrance. The objective is to identify the optimal combination of these 3 factors that maximize hydration while keeping the pH level at 7. The company has 2 concerns. They believe that the formula's consistency will not be maintained at extreme points, and the limited budget for testing the new formulas. Given these limitations, an ideal design choice is a Box-Behnken design. Under a Box-Behnken design, experimental runs are restricted to the center area. 2 factors can vary while the 3rd factor is held at the center level. A Box-Behnken design requires fewer experimental runs and is a good choice when there are limited resources. The first step is to design the experiment. Open the Design of Experiments app and click on Create Design, and select Response Surface Design. Origin offers Central Composite and Box-Behnken. We will select Box-Behnken. Click Display Available Designs. This shows the number of experimental runs that are required. Along the top are the number of continuous factors. The last row is for the Box-Behnken design. An experiment with 3 factors will require 15 runs, which includes 3 center points and 12 experimental points. The number of continuous factors is 3. Factor A is oil, and it can vary between 5 and 10%. Factor B is emulsifier, and it can vary between 2 and 4%. Factor C is fragrance, and it can vary between 0.2 and 0.8%. Next, click on Settings. The number of blocks is 1. Keep the number of center points per block at the default value of 3. Number of replicates is 1. A total of 15 experimental runs are required. Click Miscellaneous. The option to randomize the design should be used for a real-life example, but for the purpose of this tutorial, turn this setting off. Keep the default settings as is. Click OK. This loads the design table. Since we chose not to randomize the design, the run order is the same as the standard order. Under point type, 0 are the 3 center points. Notice that the levels of each factor are maintained so that 2 factors are allowed to vary, while the 3rd factor is kept at the center level. The next step is to collect data and fit the model. Enter hydration and pH data under columns H and I. Click on Analyze Design. Select hydration as the response. Click the plus button next to Model Terms and select the full quadratic model. Click on Stepwise. Select Stepwise under Method, and leave the default settings as is. Click on Plots and add Fitted Plot to the list of preselected plots. Click OK. The stepwise approach was used to remove insignificant terms from the model. The 3 main effects, oil, emulsifier, and fragrance, and the quadratic term, oil squared, were retained. The p-value for all 4 terms is less than 0.05. An adjusted r-squared of 0.95926 demonstrates that the model is effective at capturing variation present in the data. The predictive r-square of 0.92416 demonstrates that the model can generalize new data, not just fit the data on hand. The residual plots show no patterns. The effects plot shows significance for all 3 main effects: oil, fragrance, and emulsifier, and the quadratic term oil times oil. This is also reflected in the main effects plot. All 3 lines have steep slopes, and curvature shows the quadratic term, oil times oil. Click on the sheet DOE Find Y from X. Enter values for oil, emulsifier, and fragrance, and calculate the value of hydration using the fitted model. In row 1, enter 6.89 for oil, 4 for emulsifier, and 0.8 for fragrance. The fitted value of hydration is 84%. The next step is to fit a model to the second response variable, pH. Click on Analyze Design. Select pH as the response. Click the plus button next to Model Terms. Add the terms that were significant in the previous model: oil, emulsifier, fragrance, and oil times oil. Click on Stepwise, select None. Click on Plots and add Fitted Plot to the list of pre-selected plots. Click OK. Results show that all terms are significant. The final step is to optimize the response for both hydration and pH. Click on Optimize Response. Under Hydration, select Maximize as the goal. Under pH, select Target and enter 7 for the target. Click on Set Lower/Upper Limits to generate system values. Leave the other options as they are and click OK. The solution table displays the combination of values for oil, emulsifier, and fragrance where the response variable hydration is maximized and pH is 7. The prediction table shows the fitted values for hydration and pH at these values. Double-click on the optimization plot to open the interactive window. Move the red lines over the range of values for oil, emulsifier, and fragrance to obtain different desirability scores.